Hey guys, welcome back. We are getting to the end of Unit 2 and we've just got a couple lessons left, and today and tomorrow we are talking all about molecular polarity and something called intermolecular forces, also known as IMF. Today we're going to focus more on the polarity, and then tomorrow we'll talk a little bit more about IMFs to round out this unit. So let's go ahead and jump into it. So what are IMFs? So IMFs are intramolecular and intermolecular forces. And it can seem a little bit tricky, but there is a difference. So they sound the same, but they are referring to two different forces that are here in our molecules. So first, let's start with our intramolecular forces. These are going to be our covalent bonds between atoms. So those are the atoms or the bonds that are occurring within our molecules. So the bonds that we've talked about so far in this unit. The intermolecular forces are going to be the forces that are between the molecules. So the intermolecular forces are going to be the interactions between the molecules, and then the intramolecular forces are going to be the bonds between the elements. Okay, so intra means within and inter means between. So that's the distinction there. So intra is within and then inter is between. So here we can see these intramolecular forces again are these bonds that are occurring between these elements. So this is water, so this would be our hydrogen, and then our hydrogen would be the yellow, and then our oxygen would be the red-orange color here. And then the intermolecular forces would be between those multiple compounds, so those multiple molecules and how those interact. So intramolecular forces are going to be much stronger. So the bonds themselves are going to be those strong forces that help bond our molecules together and keep our compounds together. Again, this is something we're going to do over a couple of days. So this is just the intro. So if it seems a little bit tricky and we need to take some time to kind of let this settle in, we absolutely have a couple of days to do that. So that's an intro just to inter and intramolecular forces, but what we're focusing on today is something called molecular polarity. So forces of attraction, like covalent bonds between atoms within molecules, are those intramolecular forces. So again, these are the bonds between the elements, right? And they are very strong. And when we have covalent bonds, we can classify them as either being polar or nonpolar. So that is our objective for today, being able to classify those bonds as being polar covalent or nonpolar covalent. Again, the other bond choice is ionic, but we've already talked about ionic bonds. Now, if a covalent bond is polar, that means that there is an unequal sharing of electrons between the atoms. So remember, just to refresh ourselves, covalent bonds are bonds that occur between two nonmetals, and that's when electrons are shared. So in a polar bond, the electrons that are shared are unequally shared, meaning that one of the elements in the compound is going to attract those electrons more so than the other one. And then we refer to this as the molecular polarity of the molecule, and I'm going to show you guys today how to determine whether something is polar or not. So polar molecules are called dipoles, and an example here is hydrogen chloride. So we've got our little hydrogen element, hydrogen atom, and then our chlorine atom. And here is what we mean by polarity, right? So if a molecule is polar, again, one of these atoms is going to have a higher affinity for those electrons. Remember, electrons are negatively charged and they're attracted to those molecules or those atoms that are more electronegative. So if we go back and we remember our periodic trends, our nonmetals are more electronegative because remember they are more likely to attract electrons. So our nonmetal, which is chlorine, is going to be more likely to attract those shared electrons to his energy orbits. So because chlorine has the stronger pull on the electrons, because he's pulling that electron closer to himself versus hydrogen, he's going to have a partially negative charge. And because that hydrogen, that electron's getting further away from him, he's going to have a partial positive charge. So all this is saying is that the bonded electrons that are in this covalent bond, they are more attracted to the chlorine because the chlorine is more electronegative. And so when this happens, poles are created, and that's when you get molecular polarity. So all it means is that a polar molecule has an uneven sharing of electrons. And when we draw these, we usually use an arrow to show the direction of polarity. So it's just going to point towards the more electronegative atom. Again, this is going to be those molecules that are closer to the right-hand side of the table, because remember, electronegativity increases from the left to the right. So that chlorine is more electronegative than the hydrogen. So again, those electrons are pulled to the chlorine, creating a partially negative charge in the molecule. Okay, so that is for polar molecules. In nonpolar molecules, there are no poles created, and there's an equal sharing of electrons. So in this particular example, we've got chlorine gas here, which is 2 molecules of chlorine. And because chlorine is the same atom, so it's the same element bonded together, there's no difference in the electronegativity. So one chlorine atom is not going to be more electronegative than the other. They're the same element. And because there's not a difference in those electronegativities, then there's going to be a sharing or an equal sharing of the electrons. So that would be a nonpolar molecule. So it's nonpolar if the electrons are equally shared. Okay. So another thing to note about molecules that are nonpolar, they are asymmetrical. So if you were to draw your Lewis dot structures of these compounds, the symmetry of these would be off, meaning that they would not be in a straight line, basically. So they're asymmetrical. So here we have our dipole pointing to the more electronegative element, which is going to be oxygen here versus our hydrogen. This is a molecule of water, so this is H2O. Water is polar, and honestly, water is what we focus on in mostly all of your science classes, because water is the universal solvent. You guys, especially as chemistry students, need to know that water is polar, it's asymmetrical. Also, we need to know that the shape of water is a bent molecule, and we'll talk about that in just a minute. So this water molecule here has an overall polarity, again, because this oxygen is going to be more electronegative, and we're going to have these poles created, and is a polar molecule. And then if you were to draw your Lewis dot structure here, this is what it would look like, and it would be asymmetrical. And asymmetrical just means that these, when you draw it as an angle versus being in a straight line. Now, our nonpolar molecules are going to be symmetrical. So they have 2 dipole moments, and they're in opposite directions, and then the molecule itself is symmetrical. So we draw it in a straight line. So here, this is CO2, so carbon dioxide. This is going to be a nonpolar molecule, and it is symmetrical. So when you were to draw that Lewis dot structure, it would be in a straight line. So the forces in this one cancel out the dipole moment. It's 0. So there's no partial charge. The electrons are shared equally, and this is going to be a nonpolar. All right, so how the heck are you supposed to figure this out, right? Like, what is your job as a chemistry student to be able to tell whether or not these molecules are going to be bent versus symmetrical versus asymmetrical, and then trying to figure out if it's polar, covalent, or an ionic bond? That's where this table comes into play, and I promise it's going to be a lot simpler than it might seem. This is called a Pauling table. So it looks like your periodic table. Obviously, we're acquainted with that at this point in time, where we have our metals on the left, transition metals, and then our nonmetals over here on the right. The values in these chemical element boxes show us the electronegativities of the elements, right? So the electronegativities of the element, how likely they are to take an electron, right? So it makes sense that as we go from left to right, the nonmetals over here on the right are going to have higher electronegativities, because remember, they're going to be the ones to take the electrons, right? Turn into those anions. So they're more like, so the as we go from left to right, the electronegativities increase. So now let's figure out how we can calculate this to figure out if we have a nonpolar or a polar covalent. So those nonpolar covalent bonds, when the electrons are shared equally, they will have an electronegativity value less than 0.5. Okay, so what we have to do is use the Pauling table to determine the overall difference in electronegativities, and then that will tell us whether the molecule is covalent, nonpolar, or polar. Okay, so let's take a look at an example. We're going to do chlorine gas, which is Cl2, right? We want to know if this is going to be nonpolar or polar. We know it's covalent because it's a bond between two nonmetals, but we got to figure out what the electronegativity difference is, okay? So to do that, you're just going to find your electronegativity value of chlorine, and you're going to subtract the electronegativity value of chlorine from chlorine, if that makes sense, because the chlorine is the only atom or the only element in that molecule, which means the only electronegativity value we need is chlorine's electronegativity, which is 3. Okay, so we're going to do 3.0 for our first atom of chlorine minus 3.0 for our second atom of chlorine, which gives us a value of 0. Okay, so a value of 0 is less than 0.5, which means that this is a nonpolar covalent bond. Okay, if this number right here, the difference in the electronegativity is less than 0.5, that means it's a nonpolar covalent. It is a symmetrical molecule. Okay, and because it was just chlorine, anytime you have a compound or anytime you have just one atom that's bonded to itself, the electronegativity value is always going to be 0. It's always going to be nonpolar because there's not going to be a difference in the electronegativities. Okay, so now let's do one where there is a difference of electronegativities. So here we're going to do hydrogen chloride. This does have a dipole moment. But here we're going to be taking a look at the polar covalent molecule. So here is where the electrons are shared unequally. Remember, this chlorine is going to be more electronegative, so the electrons are going to be pulled towards that chlorine more so than the hydrogen. Now, when we're taking a look at polar covalency, the electronegativity value is going to be between 0.5 and 1.7. So when we go to subtract the difference between those two electronegativities, if it falls between 0.5 and 1.7, that's going to be our indication that it is polar covalent. So let's do hydrogen chloride. So all we have to do is find the electronegativity value for chlorine and the electronegativity value for hydrogen and then subtract them. We're always going to start with the highest electronegativity first and then subtract the lower one. So the electronegativity value for chlorine is right here, it's 3, and then for hydrogen it's 2.1. Okay, so 3 for chlorine, 2.1 for hydrogen. So let's go ahead and do that math. So 3 for chlorine minus 2.1 for hydrogen is going to give us 0.9, and 0.9 falls between 0.5 and 1.7, so we know that it's nonpolar covalent. This should be polar covalent. We already did nonpolar. Yeah, that says nonpolar covalent, but it should say polar covalent. That was throwing me off for a minute. So just make sure we have this right. So this is polar covalent, not nonpolar, and I will fix this in the slides before you guys have access to them, but it should be polar covalent. So again, we know that hydrogen chloride is going to be polar covalent and it's going to be asymmetrical. So just like water is polar covalent, it's asymmetrical. We know it's going to be have that unequal sharing of electrons. Okay, so just a refresher, whenever polar bonds are symmetrically arranged, they produce nonpolar molecules. And for molecules with more than one bond, polar molecules are formed when the polar bonds are asymmetrically arranged, so like water or hydrogen chloride. So nonpolar, symmetrical, polar, asymmetrical. Okay, and the last thing we just need to make sure we know is that water has a bent shape and it's got those two distinct regions of charge. So it's oxygen and it's hydrogen. It is nonpolar, so it has those partial charges on it, okay? I know this is probably